Welcome to today's lecture. My name is Apratim. I am a graduate student under Dr. Menon, and I will be giving today's guest lecture on Introduction to Geometrical Optics. To begin with, why geometrical optics is important. We know that light is primarily defined both as a wave and a particle, but for situations where we have to deal with, say, optical systems, like some of you, all of you would have in your projects when you're working on, say, solar concentrations for photovoltaics or imaging, non-imaging optics, and other things. You'll have to deal with optical systems that comprise of optical elements like lenses, mirrors, objectives, and so on. In such cases, it's often more useful to think of light as rays instead of analyzing based on the wave or the particle nature of light. And we can arrive at equations that govern the behavior of light as rays based on the formulations of geometrical optics. And so in today's lecture and in next day's lecture, we'll go over how you can formulate different equations and analyze different optical systems based on particular cases, and how you can calculate how the light interacts inside such systems. Okay, so but to begin with, let's have a quick recap of the modern view of light, which talks about the wave-particle dual nature of light. So if you talk about light in terms of particles, we have the smallest, the most elementary particle of light being the photon. It's a massless particle and travels at the speed of light, which is the highest obtainable speed in the universe. Next, if we talk about the wave nature of light, we can define a few terms. If we consider the light to be a wave, we can define the energy of a wave as equal to the Planck's constant, h, times nu, the frequency of light. We can also define momentum as h over lambda, where h is the Planck's constant, lambda is the wavelength, and nu is the frequency. Now we can put all of these two equations together and derive the dispersion relation, which equates the speed of light to the wavelength and the frequency. Next, going forward, let's analyze light with the concept of a ray. For this case, we consider light to be a wave. So imagine the light is traveling from the left to the right, and it's composed of the wave which is drawn here. So all the particles, suppose the little dots on the line, these are particles, will experience a disturbance as the wave propagates through them. Different particles at different locations along this axis experience different disturbances, and particles that experience the same type of disturbance are said to be planes of constant phase or wavefronts. So let me illustrate that just a little bit better. Suppose we have the wave going from left to right, and let's look at, say, particles which are at the peaks of the wave. So it's here, and say here, and here. We can also look at particles which are at the troughs. So here, and so on. So these particles, say this one and this one, experience the same type of disturbance. So these are in the same phase. Also, similarly, this particle, this and this would be in the same phase. So we define these planes that I just drew through the particles that are of same phase as wavefronts. So these are all wavefronts. Now suppose we go forward in time and a very small instant of time has passed, defined by delta t. The disturbance would move forward, and what we would have is the wavefronts essentially moving forward just a little bit. So let me illustrate that here. Imagine that, say, this point moves forward and the entire wave itself sort of moves forward like this, right? And so the wave is moving in this direction. So this is at t equals delta t. So you can imagine, if I don't draw the wave, I can just draw the wavefronts, and you can imagine that the wavefronts themselves are essentially moving in the direction in which the wave was moving. So direction of motion of the wavefronts. This is also to say that the energy flow of the wave will also be directed in that direction. And that is the definition of a wave. Now we come to how light would interact with matter. So the simplest case is the case of vacuum, where there is nothing to interact with. In that case, the ray of light would essentially travel at the speed of light. Instead, if you had, say, some material through which the light has to pass, and it has to interact with matter particles, molecules, and atoms, and so on, you can imagine that it would face a lot of obstructions. And essentially the light would slow down inside that material. So the velocity of light in that case would be scaled down by a factor which we call the refractive index. The refractive index is basically a measurement of how much a material slows down light traveling through it. So denser the material, the higher the value of the refractive index, the lower the velocity of light in that medium. We usually define the refractive index of air as 1, and with comparing with air, we can define materials of which are denser than air as having a refractive index greater than 1. Say glass is 1.5, it's mentioned over here, or certain materials which are rarer than air can have lower values of refractive index. The second term that we are concerned with when we speak about light-matter interaction is how much light would be absorbed inside the matter. That is defined by the absorption coefficient. In vacuum there is no absorption, so the absorption coefficient is 0. For anything else, any other materials, we define the absorption coefficient by alpha, and we define the energy that is transmitted through a length L of that material by this equation. So you can see, since this is an exponential relationship, you can see that in order to preserve the energy, or In other words, to have a medium which offers very low losses, we need very low values of alpha. So for example, when we talk about glass fiber, optical fiber that we use in optical communication, it has a value of alpha which is very low, so 0.03 per kilometers. And that essentially tells you that over a long distance you can perform optical communication without significant losses. So we can also look at an illustration of this effect, and we define this effect by the Beer-Lambert Law. You can read about it in more detail if you want. And in this case, in this photograph, we see that a laser pointer is shining light on a beaker with a certain solution of dye. So this dye is highly absorbing to the green wavelength that is shown in this photograph. And you can see that the light enters at the interface between the air and the dye, and then after a certain distance, enough of the light is absorbed so that it loses energy sufficiently to vanish into the depth of the liquid. That basically tells you that this material has very high value of the absorption coefficient, or alpha, with respect to this wavelength of light. Okay, so next we come to how light would behave when it moves from one medium to another, and essentially when it comes across an interface separating the two media. The first physical phenomena that takes place is reflection. So this is basically what happens when you have, say, a mirror and you are shining light on, say, a laser pointer at the mirror. The mirror would reflect the light back. In most cases, light is not reflected 100%, and there's always a very small fraction of light that does go into the medium, and we call that light as the refracted light. In the case of the reflected light, there's two laws that govern the situation. The first law is that the incident angle, theta I, must always be equal to the reflected angle, theta R. And the second law is that the normal, which is the perpendicular drawn to the interface between the two media, the incident and the reflected rays must all lie in the same plane. So imagine the plane here is the screen, and the incident and the reflected light must be contained within the plane of the screen. It cannot come out of the plane. The next situation is when most of the light is refracted into the system, and very small light is actually reflected back. In that case, we have another law which is called Snell's law, and that gives us a relationship between the incident angle, the angle made by the incident light to the normal, theta I, and the refracted angle, that is the angle that is made by the transmitted beam, the transmitted ray, into the second medium with the normal. The law is N1, the refractive index of the first medium, multiplied by the sine of the incident angle, equals N2, the refractive index of the second medium, times the sine of the transmitted angle or the refracted angle. The second part of the law is the same as that for the reflected, for the case of reflection, and you have the incident, the refracted rays all being in the same plane. So a more generalized situation would be so you have the interface, you have the normal, you have a beam of light coming in, part of it is reflected back, and part of it is refracted inward. So if this is my incident angle, This is my reflected angle. This is my transmitted angle. N1, N2. We have theta I equals theta R, and N1 sine theta I, equals N2 sine theta t. Okay. So this law, Snell's law, is actually very important when we will later analyze optical systems which have lenses, objectives, and interaction between, say, light going from air to glass, and so on. Next, we come to a case of total internal reflection. So this happens particularly when light is traveling from a rarer medium, that is the first medium N1 has a refractive index which is lower than the second medium N2. I'm sorry, when it travels from a denser medium to a rarer medium, so it's the opposite case. When the medium N1 has a refractive index which is much greater than that of the second medium. So imagine if the medium on the top, the first medium is a glass, and the second medium is air. So 1.5 is greater than 1. And what happens is essentially, if I go back to this diagram over here, so imagine the case for, say, total internal reflection. You have N1 greater than N2. And suppose I draw a scenario when the angle, the theta I, increases. So the ray is like this. So what would happen is this angle would also have to increase. And we keep increasing this more and more, and this will also come up. And we will have a case when this ray keeps moving upward and then sort of grazes along this surface. This is the case. This is the critical case. This is the critical condition. And for angle, so this would be your theta c, the critical angle. And for angles which are greater than the critical angle, you would have the ray going back into the medium it came from. And in that case, the law of reflection would hold. So for angles which are greater than theta c, light goes back to medium 1, which is shown here. So when you have incident angle greater than the critical angle, all of the light is reflected. When you have incident angle equals the critical angle, you have the light grazing along the interface. So then the theta t becomes 90 degrees, and you can solve Snell's law to derive this equation. And basically your critical angle becomes the inverse sine of the ratio of the two refractive indices. Next, we come to a special case of the total internal reflection, which is called the frustrated total internal reflection. So in this case, we have a scenario where you have three media with three refractive indices, N1, N2, and N3. The second medium is very, very thin. And what happens is the incident light is incident at an angle which is greater than the critical angle. So your theta I is greater than theta c, where N1 is greater than N2, like in the last case. And what would happen, if you remember from TIR that we just discussed, is that the light would reflect back into the first medium. But what happens in this case is a very small fraction of the light actually tunnels into the third medium, which is shown by this wave. This is called an evanescent wave, and by evanescent waves we mean that waves which have very, very low energy, and if they penetrate just a little bit into the depth of this medium, they will essentially vanish into a very, very small depth. It's very, very low energy wave. Most of the energy is retained in the reflected light that goes back into the higher refractive index medium, but very small amount of light is refracted in. It's not exactly refracted, so it's what it's called. It tunnels into the third medium. Okay. So going forward, we will analyze optical systems by using approximations of geometrical optics. In order to do that, we make a few assumptions. One is that the lambda wavelength of the light is very small compared to the optical systems that we will be analyzing. So suppose what do I mean by this? So the type of light that we would be dealing with is restricted to the visible spectrum. So you have wavelengths of 300 nanometers to say 700 nanometers, 800 nanometers. In comparison, the stuff that the light has to interact with is something like, say, your mirrors or your lenses or objectives, which have dimensions in the order of, say, centimeters or inches or meters. So that's quite a few orders of magnitude bigger than the wavelength of light. So the wavelength of light is much smaller in comparison to the dimensions of the objects that the light interacts with. That's the first assumption. The second one is that wave effects such as interference and diffraction are ignored. This we can do as long as the first assumption holds, that the wavelength of light is much smaller compared to the dimensions of the optical elements that it interacts with. If this was not the case, where you would have, say, optical elements of the order of, say, nanometers or microns or so on, say objects inside your MEMS devices, your microelectronic devices, your microchips and so on, we can make, we have, like, say, your transistors in your laptop, say, around 32 nanometers. So that is actually much smaller than the wavelength of light. Then it becomes much, much more complex, and you have to analyze using wave optics, where you have to take into consideration effects such as interference and diffraction. But in our case, since the wavelength of light is much smaller, those effects will take place, but we are dealing with scales which are much bigger, and the effect would be very, very negligible considered to the larger scale effects. And so essentially we can ignore wave effects like interference and diffraction. So this type of analysis is simple. The math is not as complex as you would have for wave effects, where you have to solve Maxwell's equations, but it is sufficient to analyze optical systems, which is the aim of this class. So going forward, we come to Huygens Principle, which describes how light emanates outward from a point source. And this will eventually lead to the question of what is the use of optical systems in the first place. So what Huygens Principle states is that if you have a point source, it emanates a spherical disturbance of light, which is called the primary waveform. So in case of 2D, it looks like a circle. In 3D, it's a sphere. So imagine from a point source, you have a sphere of light emanating outward. Huygens Principle states that on the primary wavefront, every point is a secondary point source. exactly similar to the first point source which gave rise to the primary wavefront in the first place. And each of these secondary point sources each give rise to a small secondary wavefront. So now imagine you have such point sources across this bigger circle, and if you trace out another circle across the smaller circumferences, tangent to the circumferences, you would have another bigger circle, and that is your secondary wavefront. And that is how the wave propagates forward. So you start with the point source, you come to a primary wavefront, then you have a secondary wavefront, and so on. As time goes on, the point source, the disturbance which began at the point source makes a bigger sphere and a bigger sphere and a bigger sphere and distributes energy outward radially. So this leads to a question as to what happens if, say, I have this point source and I'm looking at the point source from a big distance, say a fair distance away, say a few meters away. So by the time the light reaches me, the wavefront would have expanded to a huge circle. Now imagine you have, instead of a point source, a more complex object. Each point on that complex object would act as a point source, which means that after a certain distance away, what you would have is a superposition of all the different wavefronts, all the different spherical waves which have been distributed from this object. So how do you, after it has traveled a certain distance, how do you make out what the object was in the first place? We don't experience these kind of problems in daily lives because our eyes are fitted with lenses, where the lens acts as the imaging system that collects the light. But imagine a scenario, it's difficult to imagine because we are not accustomed to it, where you don't have the lenses in your eyes, and all you would see would be a superposition of all the different point sources that distributed light in the first place. And what you have is essentially all entangled and delocalized wavelets coming at you at the same time. So you have no idea what the source was, what the object was. So what the imaging system does essentially is that it collects the light that is distributed from a point source going outward, and it converges all the light back into a point that resembles the object that sent out the light in the first place. So let me illustrate that really quickly. So this is my axis. I have my say I have my object over here, it's a point source. So according to Huygens Principle, it creates a primary wavefront. Each point on it creates a secondary wavefront, and so on. So you have another wavefront and another wavefront. So these are all circles. I'm just drawing up one side of it. And the light travels outward. So now, if say I am looking over here and I had nothing to look, I had nothing in between me and the point source, what I would see is this wavefront coming at me. And imagine if the object was complex and you had different point sources, you would have a bunch of wavefronts coming at you. So you have no idea what this was. So instead, so let's get rid of all the complex points real quickly. So instead, what we can do is we can use an optical system, in this case a lens, and the lens, so let's get rid of all this, and the lens collects the light. So these wavefronts interact with the lens, and it collects the light and it converges the light. So the wavefronts converge. So this is convergence, this is divergence, and this is your optics. In this case a lens. And you have all the light coming back to this point. So that's what is shown here. Point source object, light goes outward, interacts with the lens, comes back in, and reconstructs a point image. So the aim of this lecture is to analyze what exactly happens to the light when it interacts with this optical system. And to do that, we use something called ray tracing. So let's look at the path the light takes as it travels from the point source to the point image. First, it has to cross the distance between the point source and the first plane of the lens. So in that case, it goes through a free space propagation in air. What then happens is that it has to pass from the medium air into the medium glass, and it undergoes a refraction at the air-glass interface. Once inside the glass, it has to traverse that distance, so you have the free space propagation in glass, and then it has to come out of the glass. You have refraction at the glass-air interface. Once it's out of the glass, it has to again propagate in the free space till it reaches the point at which the image is formed. So when we analyze this path, we will take up all of these situations one by one. So free space propagation in air, refraction, free space propagation in glass, refraction, and then again free space propagation in air. Okay, so now we come to a very important approximation when we want to solve these equations. And that approximation is that we will be dealing with rays which are coming toward the lens or the optical system at angles which are very, very small. So these are rays which are traveling very close to the optical axis. What is the significance of this assumption is that when in the next few slides, when we do some trigonometry and geometry to solve this imaging situation, we'll have to use a bunch of, say, sine, tan, cos terms. Of course, you know that since refractive index, refraction between two media is already involved, Snell's law is going to come into play. So Snell's law again had sine theta. So we'd be dealing with theta. Sine theta. Under the paraxial approximation, we can assume that sine theta is almost equal to theta if the angle theta is small. So in this case, we are using epsilon. So if epsilon is very small, we can assume that sine epsilon is epsilon, tan epsilon is epsilon, and cos epsilon is 1. So if you want to look into what causes this, we can quickly check the Wikipedia entry on small angle approximation. So that's what I was just talking about, is that sine theta becomes theta, tan theta becomes theta, and you have, this is, you can, if you want to go through, you can go through the Taylor series approximations that are given in these articles. But I like to look at this graph over here, which shows you in the x-axis the angle in radians, and in the y-axis a certain function of that angle. So the red line is of x. So angle versus, so x equals x. So that's essentially a straight line. It goes from 0 to 1 in the x-axis and 0 to 1 in the y-axis. Then if you plot sine, so as in y equals sine x, that's the green curve, and if you plot y equals tan x, that's the blue curve. And you can see that for this range, the three graphs follow very close to each other. So that would be that for certain angles, 10 to 30 degrees or less than 1 radian, this approximation is valid, that sine and tan are approximately equal to x, or theta in this case. So this graphical way, I prefer this graphical way, and then you have the same thing for cos, if you want to look at that. So we can assume this case is correct and move forward. So the paraxial approximation. The other assumption that we are going to make is that we can actually ignore, so if the light is traveling very close to the optical axis, we can ignore the difference between this arc and the height at which the ray hits the glass. So actually I think it would be more helpful if I illustrate that. So paraxial approximation, sine epsilon equals tan epsilon. Also, the case of the arc length, that is, so if this is your optical axis, and say this is like one side, so you have glass over here, and there, and this angle is very small. What happens is we don't make a difference between, we ignore the difference between this point, so let me mark that with red, and say this point. So essentially this difference is very small and we can ignore that. Why this is important is because if you do a little bit of geometry and assume, say, this is the center, so this is essentially your radius of curvature. So now let me mark this height as h and this arc as s. So you can, if you remember your geometry, you have s equals r times theta. Theta is this angle. So what happens in the paraxial approximation? Is that h equals s. because we ignore this distance. So we set h equals the arc length. So this is very helpful, because then from geometry, if you don't know the value of h, or sorry, if you want to relate the value of h to the value of, say, the radius of curvature r and theta, you can use the approximation of s equals r theta, as that is the same value as h. So this is important. The other important thing that we would require when solving the next equations is Snell's law. Okay, so let's keep that in mind. These two are what we would primarily need. Right, so let's go on and analyze the system. And first, let's just take a very simple situation when you have light from a point source, which is in the first medium, say of refractive index n, going into a second medium of refractive index n prime, and the second medium is suppose of higher refractive index, let's say glass or something. So imagine this is half of a glass sphere. That would essentially this would essentially show you what happens when light interacts with a curved interface separating two media of different refractive indices. We have all the assumptions that we previously described holding true in this case, and like we discussed previously, in order to analyze, let's look at what the ray does as it travels this distance. First, it has to go from the point source to the interface, so that's free space propagation. Then it experiences refraction at the interface, so that's refraction. And then it would have to travel a further distance into the second medium, so that's free space propagation. So we have three actions. And now let's analyze and do the math. So if you solve the math, it gives you these equations. So I'm going to work it out, and let's see what we get. So this is my optical axis. So this is, say, my interface, the glass interface, the curved glass interface. So this is medium 1, N1 is the refractive index, medium 2, N2. And since this is a general case that we are solving for, let's just assume that the point source is not at the optical axis, instead it's at a height above the optical axis. So, point object, and we have this ray of light going out. Of course, like we mentioned, the ray makes an angle, say alpha naught, alpha 0, and alpha 0 is very small. With the optical axis, the angle with the optical axis is very small. It's at a height of x0, x naught. You can refer to the lecture notes for this case. This is what is described in lecture notes. And then you have the ray of light bending inward, so that would be, let's see, okay. So let me draw the parallel to the optical axis over here, and it would essentially move into this medium. So this will be and suppose it has now arrived at this point. That's the ray has arrived at this point. So let's define this point using a height x2 and the angle the ray subtends. So the optical axis again. Extend this. So it's a okay, and this is say your alpha 2. So this is the initial position, x naught alpha naught. This is their final position, final initial. Right? So we want to see how x2 and alpha 2 are related to x naught and alpha naught using the rest of the parameters in this system. So what are those parameters? So let's define this distance. Let's call that d01. Let's define this distance. Let's call that d12. So firstly, for free space propagation, you have, so this is your, so let me quickly note that down. So this is your free space propagation. This is where you have your refraction. This is again your free space propagation. So assume the first free space propagation takes place. The ray is at this point. So let's define that point by say a height x1 and an angle alpha 1. Then after the refraction takes place, the ray is on this side, on the medium 2 side. Let's define that angle as x1 prime and this angle as alpha 1 prime. Okay. Lastly, we define the radius of curvature. The center. We define the radius of curvature as r. And then let's see how we can solve this problem. So we want to find out how x2 and alpha 2 are related to x naught and alpha naught. So firstly, I'm going to write the equation for the free space propagation. So free space propagation. So what happens? Let's look at the height. So x naught and x1. So let's look at this triangle over here. And what you have in this triangle is, if you take the tangent of alpha naught, you have tan alpha naught equals this height over here from this point to this point. So let's call that h over d01. We have the axial approximation, so tan alpha naught becomes alpha naught and your h becomes alpha naught times 1. So your x1 is essentially h times x naught, which is, so I'll put the x naught in the front, plus alpha naught d0 1. Let's see what's wrong. What happens to alpha naught and alpha 1? So let's now relate this with this. It doesn't change. So the ray was traveling in this direction. So there's a change in the height of the ray, but the angle hasn't changed because refraction hasn't taken place yet. So alpha 1 equals alpha naught. So that's your first set. Now let's do the case of refraction. So I'm just gonna use this real quick so it's supposed to work. So refraction. So let's solve for that, and firstly what we would like to do is write down Snell's law. But Snell's law is defined with respect to the normal to the interface. So let's take a look over here. So we have the normal, and we define theta t and theta I with respect to the normal. So what is the normal in this case? So the normal in this case, if you remember, if you have a curved surface and you draw the tangent to that surface, the normal to that tangent is the radius. So we define our angles with respect to the radius. So this is your theta I incident angle, and this is your theta t transmitted angle. So with respect to this, if we write Snell's law, we have n1 sine theta I equals n2 sine theta t. For axial approximation, n1 theta I equals n2 theta t. Okay. Now, what are we trying to find out over here? How we can relate lambda 1 with lambda 1 prime? That's the change in the angles. First, let's write down the relationship between the heights. So essentially, the height doesn't change. The ray was here and the ray exited. So the ray was here and the ray exited from here. So essentially, x1 and x1 prime are same. So first, let's write down. Let's just remember that, and we'll put that down later. So the angle is what changes here, and we have to do a fair bit of geometry to solve that. So we are looking for alpha 1 prime. So what is alpha 1 prime? So alpha 1 prime, we can see, is, so let me define this angle as A. So based on that definition, alpha 1 prime is theta t minus A. Now we make use of the parallel lines rule of angles, alternate angles. So if this is angle A, this will also be angle A. Now we will make use of this arc length relationship. So if this was theta, remember you had the height times the radius of curvature, and the theta in this case is A, and the radius of curvature is R, and your height is x1 prime. So we can write A as, so you had S equals arc theta, or in this case x1 prime equals A R, so your A becomes x1 prime, so let's minus x1 prime over R. So remember, this is because x1 prime equals A R. Alright. Now let's relate theta t with theta I. So from the above equation we can write, of Snell's law, we can write theta t is n1 over n2 times theta I minus x1 prime over psi. So now let's see what theta I was. Okay. So theta I, so I'm just going to extend this optical axis back over here, and you have theta I equals, so if I define again a hypothetical angle, say this one as B, and from your alternate angles pool, this angle is again alpha naught. So theta I was essentially B plus alpha naught. So let's write that down. Okay. So now let's look at what was B. So if we see over here, so I'm going to pick another color over here. So if we see over here B, so look at this line and this line. So your A is equal to angle B. So keep in mind, so we're looking at, so here's this, and this was the R, and this was your optical axis, this was your A, and this is your, in this case. So we solve that, and what we write is N1 over N2 times, so we have A plus alpha naught, we already know is equal to alpha 1. That's what we previously solved. So I'm just going to put that there because we are trying to relate alpha 1 prime with alpha 1 minus, and what was our A? So our A was x1 prime over n. So this, so you get n1 over n2. I was calling this n1 and n2 right here. N1 over n2 times alpha 1 plus n1 over n2 minus 1 times x1 prime over r. So if you solve the part in the parentheses, you get n1 minus n2 over n2. So that was your, this is your alpha 1 prime. Also, we remember we said, we already derived that x1 prime equals x1. So that's your set of equations for refraction. And lastly, we have the case for the second free space propagation, that is the same as the first one. So no change in angle but change in height, and just like I worked it out for the first one, I have x2 equals x1 prime plus d12 alpha 1 prime, and alpha 2 equals alpha 1 prime. So that's a set of equations. So now let's go back to the slides. So if you want to compare, these are the equations that we just derived for the propagation free space, first propagation, refraction, and then the second propagation inside the second medium. So now, if we put all of the equations together, we can write the big equation that defines x2. And we can also write the equation that defines alpha 2. So there's not much space over here, probably. Let me try to write equations over here. So we had x2 equals, so what do we have? What did we solve? So x2 equals x1 prime plus d1 to alpha 1. So x1 prime, which was equal to x1. So x1 plus d1 to alpha 1 prime. Alpha 1 prime we solved was n1 over n2. So let's put that over here. Alpha 1 plus n1 minus n2 over n2 times x1 prime over r. Now we have to replace x1 prime, which was x1, but x1 is then related to x0, so let's write that. So x1 plus d1 to n1 over n2 alpha 1 plus n1 minus n2 over n2 times x1 prime, which was x1, which is related to x0 as, so I'm just going to write it here, as x0 plus alpha naught d0 1 over r. So that is your x2. Your alpha 2 was alpha 1 prime, and alpha 1 prime we have already defined, but and we can simply put in the value of x1 prime over there. So alpha 2 becomes equals to alpha 1 prime equals n1 over n2 times alpha 1, which is equal to alpha naught, plus n1 minus n2 over n2 r times x1 prime, which is equal to x1, which is equal to x0 plus alpha naught d0 1. So now if you solve this, rearrange the terms. So I'm not going to do it here because I don't have much space. So solve and rearrange. You should see what you have in slide 23. Equations. Okay. So that way we can relate the height x2 and the angle alpha 2 with the initial height x0 and the initial angle alpha naught subtended with the optical axis. But really, so after working through this, what did we arrive at? So what we managed to do was really write a bunch of equations that describes what happens to the ray of light from its initial position to its final position. But going forward, we will see how we can use this to solve actual optical systems. But in this case, so let's see. So keep in mind that this was a very, very simple case where you had just a curved glass surface, or say a curved surface of a different refractive index medium, and another refractive index medium that the ray was coming from, and that's it. That's what you just solved for. But it showed you how the light would interact with a spherical surface. In the case of a lens, it would be more complex because you would have, say, an exit interface where the light would come out of the glass, and then you would have the image forming on the optical axis. So if we had to write these big equations for just this simple case, imagine the equations that we would have to deal with if we had to solve for that, the more complex situations. So in that case, we will work with something called matrix formulations, where we use matrices to solve these equations, and you'll see that it is actually much easier than it looks. But we have to keep in mind a few sign conventions as we do the math, and these are basically a certain set of rules that you have to keep in mind when you're solving. So the first one is that light travels from left to right. That's what I was drawing so far, and that gives you positive distance. So from left to right is positive, from right to left is negative. Radius of curvature is positive when surface is convex towards left. So if you have this convex surface, you have positive radius of curvature. If you have a concave surface, it would be negative radius of curvature. Also, that would mean that if the radius of curvature is convex to the right, that would be negative. So like a mirror image of what you have. It's flipped, horizontally flipped. Longitudinal distances are positive if pointing to the right, and lateral distances are positive when pointing up. Ray angles are positive if the angle is measured by rotating the ray counterclockwise, and if you rotate clockwise, it's negative. Okay, so now we come to a special case where we have on-axis image formation. So for on-axis image formation, what we have is, if you look at this case, you basically have a point source which is located on the optical axis. So your x0 equals 0, no height, and there is some optical element. It's a lens, but let's assume there's something that makes an image of the first point S to a point P on the optical axis. That also has no height, so x2 equals 0. So in these equations, we can use the relationships x2 equals 0 and x0 equals 0. We have the rest is same, and then if you solve for that, you can derive this equation. And this is basically similar to something that we learned in high school, where we had 1 over the image distance. So in this case, it's not 1 because we have a certain refractive index, say n prime, over the image distance, which is d12, plus n over d01, which is the object distance scaled by refractive index, equals, if you remember what we had in school, that would be 1 over f. So if you solve the equations, I suggest you go ahead and do the math. Solve these under the certain conditions and derive at this. You had 1 over f. So obviously here you don't have 1, you have the refractive indices. But this equation, this relation, the term on the right, that is essentially a 1 over f, which is called the power of the lens. So n prime minus n over r is equal to 1 over the focal length. Okay, so this is a second special case, which is the case of an image of point object at infinity, and let's work that out. Okay, so to work that out, what we would have is, if we look at this case that we solved, if you had light coming from a point source at infinity, we assume that the rays are traveling parallel to the optical axis. So if the rays are parallel to the optical axis, there is no angle to begin with. So for your previous case, your alpha naught would be 0, your alpha 1 would be 0, you'd simply have to work with alpha 2. So you put those assumptions in these equations, and you solve for we solve for the point, the distance at which the light is focused. Okay. So I have a new canvas over here, and I put the generalized case that we solved for. I put the geometry over there. I removed all the equations that I worked out. I put the final forms of the equations, and I've drawn our case. So this is your point object at infinity case. So you have the parallel rays traveling, the rays parallel to the optical axis, focusing at this point. Right. So we, like I said, we don't have the x2 equals 0. We don't have alpha naught, alpha 1, that's equal to 0 because the rays are parallel. And so if we plug this in to the equation of x2 in the above case, what we have is, so x2 equals 0, so we have 0 equals d01, and alpha naught is 0, so the second term goes away, so that's not there. So the first term we have, so I changed the refractive index notations from n1 and n2, what I was using previously, to n and n prime. That's then now it's similar to what we have in the slides. But the idea is the same. d12 plus 1 times x naught. Right. And for the angle, we have alpha 2 equals n minus n prime over n prime r x naught. So we have a finite height x naught, yes. So if we now solve for these two equations, what you can get is your d12 equals minus n prime r over n minus n prime. So if we formulate that, that's n prime r over n prime minus n. And this is actually now, if you recall, parallel lines coming to converging to a point. This is your focal length. So this we had already learned as a definition when we were in high school, that the focal length of an optical system or lens is the distance from the interface at which parallel lines or beams coming from infinity are focused. But in this case, what we did was we defined the focal length in terms of the refractive indices n prime and n, and the radius of curvature r. Because those are the parameters with which you can work when you're constructing an optical system. You have your surrounding medium, you have the medium in which you're constructing your optical system, which is n prime, and then if you're making a lens, you can define its radius of curvature r, and so on. So that way, using these three parameters, you can determine what the focal length of your lens would have to be if you had to focus parallel beams. Okay, so yeah, so what I was saying is that this is the definition of the focal length as we have previously learned, and that's all that what we did here was define the focal length in terms of the refractive indices of the two media, n and n prime, and the radius of curvature of the optical system. So that's all you need to build an optical system. You need to know the refractive index of the surrounding medium, you need to know the refractive index of the optical system, and the radius of curvature, say if you're designing a lens, and so on. So this is focal length f. So this is a very, very important relationship. For the next case, when you have the reverse, as the object is placed at the focal point, you have parallel rays coming out of the system. So it's the same derivation except the other way around. So you can try that by yourself. And I'll move on to the matrix formulation. So this is the next important part of the lecture. And so let me work out the matrix formulations on this side. So the way the matrix formulations works is by relating parameters on two sides of the optical system. So say on the left you have parameters which define the situation when the ray comes out of the optical system. So that's your refractive index on the outside, the angle the ray makes on the outside, the height outside, and that is related to the optical system defined by a matrix M with these, say, 4 elements, M1, 1, 1, 2, 2, 1, 2, 2, and the same parameters just on the other side when the ray was entering the system. So what does that mean? So let me draw the case real quick. So suppose you have the optical axis and you have this say this ray going in this direction, and the ray then goes out of a certain optical system. I'm not going to define what it is. Let's just assume it's an optical system M. And initially the ray is defined, so this is your optical axis, so this is your alpha. Say the ray is at a height x, and on this side the refractive index is n. So one usual way to define a ray using a vector is by using its angle and its height. In the case of optics, we scale the angle with the refractive index, so we can write n alpha and x as the definition of the ray. Similarly, on this side, the ray has, suppose, a height x and another angle alpha. So there's no point calling them the same angle, so I'll put this as alpha out because this is coming out of the system, x out. The refractive index on this side is, suppose, n out. This, let's put n in, alpha in, and x in. If that is the case, what we can write is the final vector defined as n out times alpha out over x, it's not over, it's a vector, so x out equals this optical system matrix M, actually, so this optical system matrix, let's say it has 4 elements, M11, M12, M21, M22, times n in, alpha in, x in. How is this useful? Let's take the case of when a ray is simply propagating in free space. So say part 1 of this problem, free space propagation. So just the ray going from here to this point. So let me draw. So suppose we have this. So initially the ray was here, and after a certain time it moved to that point. Optical axis, the actual optical axis. Suppose this is height x0, this is height x1, this is angle alpha naught, this is angle alpha 1, and this distance is 0, 1. First off, before we solve anything, let's just put down what we already did before. That is this height over here, just this height is equal to d01 times alpha naught. Comes from the tangent. Tan of alpha naught equals that height over d01 per axial approximation. Tan alpha naught becomes alpha naught. You multiply it with d01 and you get the height. Let us just write the matrix multiplication, matrix formulation like we defined. So everywhere over here is the same medium, so it's just n. So n out would be n, alpha out would be alpha 1, x out would be x1. Instead of the four elements as m, 1, 2, I'm just going to quickly put down a, b, c, d. n in, still n, alpha in is alpha naught, x in is x naught. Let's do the matrix multiplication. A times n alpha naught plus b times x naught. C times n alpha naught plus d times x naught. And so if you equate the terms, you get n alpha 1 equals a n alpha naught plus b x naught. And x1 equals c n alpha naught plus d x naught. But we know that alpha naught is equal to alpha 1 because the ray simply did free space propagation. There was no change in angle. So we can also put that down here. Right? And that means from the first equation we can write, first off, just by looking at it, since if your alpha 1 is equal to alpha naught, b equals 0. And we can cancel n and n and write a equals 1. Right? From the second equation, we can write x1 equals c n alpha naught plus d sorry, we do that. So we had x1 equals d01 alpha naught plus x naught from the geometry. So x naught, just want to write that down over here. So this is x naught plus d01 alpha naught, and that is equal to what we had here, 0. So again, just by looking at it, d equals 1, and if you solve for c, you get alpha naught cancels out, and you get c equals d01 over n. So what is your matrix? Your matrix ABCD now becomes 1, 0, d01 over n, and 1. So that is your free space propagation matrix. Translation through uniform medium. That's that. You have your input conditions, you have your output conditions, and that's the matrix. Why is this important? We'll see in just a while. Let's just first look at refraction by the spherical surface condition. These are your two basic cases. So I'm going to put this down. This is free space propagation, and here I'm going to do refraction by spherical surface. Okay? In that case, we have the optical axis and we have our spherical surface, and we have the beam coming in, refracted inward, like that. And in this case, there is no change in height because the interaction takes place at the interface. So remember, this is the height, x1 on this side, x1 prime on this side, but essentially the same. And you have alpha 1 prime and alpha 1, the two medium n prime and n. Now let's just write down the matrix formulations. N out in this case is n prime, alpha out is alpha 1 prime, x out is x1 prime, equals, I'm going to write A, B, C, D for ease, and n times alpha 1 x1. Do the matrix multiplications and write A n alpha 1 plus B x1, C n alpha 1 plus D x1. Additionally, we know that x1 equals x1 prime. So from these three, just by looking at the second equation, if x1 equals x1 prime, C has to be 0. So this term cannot exist. So just directly write C equals 0, D equals 1. From the first term, we have to then now go back to what we did previously and use the radius of curvature to solve this equation. And what I'm going to do is very easily just go back to what we did previously and look at what alpha 1 prime was. So alpha 1 prime was n1 over n2, alpha 1 times this second term over here. And that will look very familiar in this case when I simply divide the first equation by n prime. So that the alpha 1 prime would be A times n over n prime alpha 1 plus B over n x1. Now if you compare the previous equation, in the first term there was only n over n prime alpha 1, which gives you A equals 1. In the second term there was n prime minus n over nr times x1, so that gives you B equals n minus n prime over r. And that's it. That's your matrix. A equals 1, B equals n minus n prime over r, C equals 0, D equals 1. So refraction at spherical surface matrix. That's it. These are the two things that you have to keep in mind to solve any complex optical system. Let's look at how. So this is the matrix I just derived. Now let us look at the big problem that we were solving using all the geometry and trigonometry and whatnot. So in this case, all you have is you look at the final condition x2, write the final matrix, go back, retrace back. So first you have D1, propagation through D1, 2. So write a translation through D1 to matrix. A refraction at an interface, write a refraction at the interface matrix. And then translation again through D0, 1. Write the matrix for that and multiply it with, the initial conditions, the last matrix. Simply put these two matrices that we derived for translation and refraction in these places. Replace your D01 by D12 where you have 2 in the first case, and put your appropriate values for n, refractive index, n prime, refractive index, and radius of curvature r. Do the matrix multiplications, and in a couple of steps you can get the same equations that you have to do all the geometry and all the trigonometry to derive. This also holds true if you have a convex lens, a concave lens, different types of interfaces interacting, different complex optical systems. You can write the same matrices, just change the values of D01 or n or r and n prime, do the matrix multiplications, and you'll have your equations. That's why matrix formulation is such a powerful tool when it comes to solving complex optical systems. We can look at an example for a thin lens, but yeah, let's just do this in the next class. I'll keep it at this at the end of the matrix formulation. So you can go over the equations that we derived and how we derived the matrix formulations and justify that that gives you the same result as doing all the geometry and trigonometry would give you. And just go over the equations and the derivations in detail, and we'll take up the rest of the lecture notes in the next class. And we'll look at different optical systems and different examples. Okay, thanks.